Go team. Okay, so now we're going to talk about energy. So we are at, what is this? This is 2A, Focus 2, Section A. So diving into the first law of thermodynamics, we need to talk about energy a little bit before we can do that. So we've got forms of energy, so 4 different forms of energy: heat, mechanical, kinetic, and potential. And just to give you a sense of how we quantify heat, mechanical, kinetic, and potential, so for heat energy, we're going to have that associated with temperature. Mechanical, we're going to associate that with a pressure. Kinetic, we're going to associate that with, speed. And the potential is going to be some sort of configuration. So between all of these, we really care about how do we quantify energy. And as we'll see, you've got joules on one side, you've got joules on the other, but these joules are going to represent different types of energies. And so when we've got the energies of quantum states, for instance, that's really dealing with potentials, the configuration of the electronic interactions and the electrons within their subshells and their orbitals and stuff. Those energies are going to be a configurational entropy. When you've got, Newton's law, F equals ma, and you're throwing something, you've really got a kinetic energy that you're looking at. Mechanical energy, that pressure, force per unit area, there's an energy associated with that. And likewise with heat energy or thermal energy. So this is going to be our main focus, okay? Temperature and pressure, or heat and mechanical energy. So pause. Okay, energy. What is energy? From our discussion on the first day of class, hopefully you have a better sense of what energy is, but I want to put it into a concise definition. So the capacity for a system to do work. And so work is going to be the energy associated with the action of a force. Okay, so work energy associated with the action of a force. And as we already talked about, work is equal to force times distance, where here you have newtons, and here, unit analysis, you have meters. So if you put a force over something, I would normally have a chair in front of me, but I don't because I'm not in the classroom. So I have my coffee mug, and actually, well, you can't even see it. Force across a distance. So I'm pushing my coffee mug across the table. And so there's a force across that distance. That's the work energy I'm putting in. And you might chuckle to yourself and like, oh, Allison's little choreographic dances of things. I swear to goodness, I want to see, well, I won't see you when you're taking your exams because we are apart. But you should really act out some of these things to kind of really understand fundamentally what these things are representing. Force across a distance. You're putting work energy in. Helps to visualize. Okay. So this is the classical idea of energy. Then you have the atomistic idea, which is that you've got the organized, so if you've got a system, back to the standard box of gas particles, and you've got some sort of organized system, as in here's the gas particles, and then you put a force across them, that force is going to have them all moving in the same direction, such that if your hand goes, you blow on your hand, you are putting force against those air particles and also contributing some yourself, or you can even do it like this. And so if you do this, you can feel, I mean, I'm not hitting my hand, but I can feel those little pulses from every time I wave. That's creating a force. And so there's an organized migration of atoms moving in one direction. You blow up a balloon, the same idea. You blow up the balloon expands. Those air particles or air molecules are pushing against the external boundary of the balloon, work energy. You can feel them going in one direction. Energy transfer, making use of the organized motion of atoms. So this is the classical idea, and then here's the atomistic. And I will write this out just so you have it for your notes. The energy transfer, making use of organized motion of atoms. Energy transfer, making use of organized motion of atoms. Okay. Work. That is work. Work. Go team. Now let's heat things up a bit. Get it? Heat things up. Love it. Okay, so heat is the energy change as a result of a difference in temperature. Okay, so the energy change due to a difference in temperature. So another way to think about this is energy transfer through thermal motion. So there is a importance to think about the scattered. Okay, so here are all my gas particles, and if I were to blow on them or wave them in some way, like fan them, they're going to move. There's going to be a mass migration of them to one side. If there's a little candle, and so I'm putting heat energy in, so I'm adding heat energy. As I put heat energy in, high temperature, low temperature, there's a thermal gradient. There's a difference in the temperature between this side and that side. That's going to cause an energy flow, energy transfer through thermal motion. The particles down here are going to gain the thermal energy before the particles up here. And then these are going to increase their speed. They're going to start to really bounce around more and more. They're going to transfer their energy, and you're going to have the subsequent transfer or migration of thermal energy from the temperature difference, also known as a temperature differential, between the hot side and the cold side. Cool. Heat energy, utilizing differences in thermal motion. High thermal motion, low thermal motion, as in hot and cold, as opposed to work energy, fanning the flames and moving those and getting all the molecules to move collectively. Go team. Heat, work. Okay, before we can get into combining heat and work together to understand the first law of thermodynamics, which is where we're going, I want to define the system, or defining the system. So how do we do that? Well, there's three types of systems that we can have. And we talked a little bit about systems on day one, but now I want to give us specific definitions. We have open, closed, and isolated. Okay, open system. So we have both heat and matter. And actually, I'm gonna pause. I got colored markers. Hooray. Okay, so we've got heat, blue, and matter, or atoms and such, is purple. All right, so for an open system, both heat and matter can be exchanged with our system. Cool. For a closed system, we've got heat that can be exchanged, but matter cannot. Okay, so no matter. Isolated system, any guesses? Both heat and matter. Nope. So what is this? So both are not able to exchange. So no heat, and no matter. Exchange, completely isolated, and exchanged with what, you might ask? Well, like we talked about before in class, we're looking at the system, and then there's the surroundings. So the surroundings represent the things in which the energy exchange is occurring between the system and the surroundings. And then if you want to, so here's our surroundings. So you can have an open system with surroundings, but then if you want to look at the entirety of both the system and the surroundings, this is where you will look at the universe. And it is not the universe as in the expanse of the cosmos, beyond the local group, way outside into the fabric of time and space when they've merged. No, it's really just the cup is my surroundings, the coffee inside, I don't even know if you can see, whoops, go team. The coffee inside is my system, the cup is my surroundings, the universe is the mug plus the coffee. That's the universe. My mug of coffee. Hooray. Cold coffee. It's like 3 o'clock in the afternoon right now. It's very cold coffee. Ugh. Okay. Cool. System open, closed, isolated. We're going to start here. This is the simplest. We're going to assume nothing can get in and nothing can get out of our system. We're going to start here, develop the laws of thermodynamics. We'll then play here. We won't go here. This is hard, especially, here's a spoiler alert, especially when your system is open. What I mean by that is that let's say that you have some, I can't even think of a reaction, N2 plus, oh goodness, N2O2. Is that right? I think that decomposes into nitrogen and oxygen. I can't remember, whatever. This is why I don't write chemical reactions on the board. A plus B yields C plus D. If you have a chemical reaction occurring, you technically have an open system. This is your system. It's going to change and open itself up to creating new compounds. And the other thing is you have a deficit now because you're losing reactants as you're gaining products. We will be representing those types of things thermodynamically. But how do you take into account the fact that N is changing? You assume an open system. Cool? So that's where it's really important to think about these with every problem that we approach. And that's why we're going to start with the simplest one, which is an isolated system. Go team.